Okay, over here, if n equals 0, so I know that, if it's n over 0, so I know this is going to either be plus infinity or minus infinity. So now it really matters what side I'm on. So let's take a look. We're going to split this into two-sided limits. The limit as x goes to the negative side of 2, and again from the positive side. Now, what do I know? I know that this is going to be plus or minus infinity. I already know it's an infinity. I really just need to know what the sign is. So in that case, I find the easiest thing to do here is to pick a number that's just below 2, just to the left of 2. So I'm going to say x equals 1.99. And over here, I'm going to pick something just a little bit bigger, 2.01. This is in a way like a sign chart. I'm not interested in the exact number. I just need to know the sign. I already know the answer is infinity. I just need to know which one. So if I put in 1.99, that's positive, that's negative. So it is like a sign chart. Positive over negative, that means negative infinity. If I put in 2.01, that's positive over positive. So this would be positive infinity. So when I look at these two, they do not agree. They are not the same. So that means my original two-sided limit does not exist. Okay, and so basically this is going to be this is going to be a rational function with a vertical asymptote at 2, and it's going in different directions. Okay, let's look at another example. Let me mix these up a little bit. All right, so here's one. Limit as x approaches infinity of minus 2x cubed minus 4x. Okay, so look over here. We're not in the x approaching finite value. We're in x approaching infinity. So we need to look at only the leading terms. So we know that this will be equal to the limit as x approaches limit as x approaches infinity of negative 2x cubed. So remember, these are not the same when we graph them. They're not exactly the same. But we're not worried about that. Limits are all about behavior. So the behavior of this one and the behavior of this one are the same at x equals infinity. So when I put in infinity, I'll get infinity cubed. Okay, that's still a big giant infinity with a minus sign on the front. So the minus sign matters. The 2 doesn't, but the negative sign does. Okay, let's look at this one. Limit as x approaches infinity of x cubed plus 2x minus 1 all over 3 minus 8x. Okay, this one is in the same spot. I'm looking at it as x approaches infinity, so I'm down here. I want to rewrite with only leading terms. Leading terms are not the first term. Leading terms are the term with the highest power. So this would be equal to the limit as x approaches infinity. Leading term up here is x cubed. Leading term down here, negative 8x. You have to include the coefficient as well. Okay, simplifying. X is canceled. X squared over minus 8. When I substitute in infinity, I get infinity divided by a negative number. So again, the 8 doesn't matter, but the negative sign does. So this will be negative infinity. So just be aware that the order may not be in descending order, so you just need to always pick the one with the highest power for leading terms. And then remember the negative signs do impact, but multiplying by a constant does not. Okay. All right, one more. Limit as x approaches 3 of negative 3x over x minus 3 quantity squared. Okay, so again, first we're approaching a finite number, so we're here. The first thing we do is try to plug in 3. So we'll get minus 9 over 0. Remember, if it's a finite constant number, we're done. That's not here. If it's 0 over 0, that means we have a hole in the graph. We have to do some factoring and canceling. That's not here. We have n over 0, which means this is going to some plus or minus infinity. We don't know which. So it may be different on either side, so we need to check. So this is where we're going to split. And we're going to have two different limits. One as x approaches 3 from the negative side, and one as x approaches 3 from the positive side. Okay, so again, we know they're going to infinity. We just need to know plus or minus. So a little bit like a sign chart. So what is a number a little bit less than 3? 2.9? And what's a number a little bit bigger than 3? 3.1. You could use 2.99, 3.01, just something close. Okay, so if I put in 2.9, I get minus times a positive, minus plus in the numerator. Denominator, anything squared is always positive. So altogether, I would get negative infinity. Looking at 3.1 here, I'm going to get a negative and a positive in the numerator. Square is always positive. So also negative infinity. These agree. They are the same. Therefore, two-sided limit is that value, negative infinity. And again, I know negative infinity is not a number we can write down, but we know from both sides that this is going to negative infinity. So we know the behavior. We know what's happening as x approaches 3. It's going to negative infinity no matter which direction you come from. So that's why the two-sided limit exists. Okay, let's do a little bit of asymptote work, and then we'll do a little bit of word problems. Okay, so here's one. Find the asymptotes. And here's our first example. F of x equals minus 3x over x squared plus 1. Okay, we know how to find vertical asymptotes. Vertical asymptotes are where the denominator equals 0, which in this case is never, right? This, if I try and set it up and solve, I get no real number, so there is no vertical asymptote. Horizontal asymptote, though, I can actually write this as a limit now. I know how to do that. So let's employ some calculus. The limit as x approaches infinity of this, negative 3x over x squared plus 1. Okay, now I can take only leading terms. So the limit as x approaches infinity, negative 3x, include the coefficient, x squared in the denominator. Okay, I can go ahead and cancel. So limit as x approaches infinity, negative 3 over x. Go ahead and substitute in again. If I put a very large number here, negative 3 over a huge number is 0. So that means that my horizontal asymptote, I should always write a line. Remember, these are y values, so the horizontal asymptote is at y equals 0. Okay, so that's that one. Let's look at one more. X squared plus 4x plus 5 over x squared plus 8x plus 15. Okay, so we know we're going to need to do some factoring on the denominator to get vertical asymptotes. Let's go ahead and factor the numerator while we're at it. So x, this would be 3 and 5, so x plus 3, x plus 5. And here, 4 and 1, I see. No. I have written something down incorrectly. This is a minus sign. There we go. Minus 5. So, x plus 5, x minus 1. Okay, so the first thing we want to do always, I know it's not part of the problem, but let's go ahead and get the denominator. we know that x cannot equal -3 or -5. Now, are they both vertical asymptotes? Well, if we were to write the limits, if we were to write this limit as x approaches -3, we would find that that goes screaming off to infinity. That's one of the infinities, if you do the work. So now let's look at this one. As x approaches -5, when I put that in, I'm going to get 0 over 0. So that's indeterminate. So not every place the denominator is equal to 0 gives us a vertical asymptote. And you can tell that if you actually do the limits. If you think there's a vertical asymptote here, go ahead and set up the limit, and you can evaluate it. Or the other thing that we know is that if these cancel, we can rewrite this way. X minus 1 over x plus 3, knowing that x cannot equal -5, because that was part of the original domain. Okay, so now we can look at writing out our vertical asymptotes. Those we can write out a little bit more quickly than using limits. So vertical asymptote, we know would just be x equals -3. X equals -5 will be a hole in the graph. That's the one that gave us the 0 over 0. Now let's look at horizontal asymptotes. Again, we can write the limit as x approaches infinity. We can use the simplified version. That would be fine. And we'll also look at using the non-simplified version. So here, so we can look at this. So this is the same as taking the highest leading terms. So x over x is 1. That whole limit will be 1. We could also, so in the end then, we have y equals 1 as a horizontal asymptote. We could also look at the original problem, this one here, x squared plus 4x minus 5 over x squared plus 8x plus 15. Again, looking at only highest powers, we would look at the limit as x approaches infinity of x squared over x squared. X squared over x squared is 1. So either way, it doesn't matter. Okay, so we have domain, vertical asymptote, and horizontal asymptote. All right, now let's look at some problems from the book. We are in section 2.2. I'm going to look at problems 86 and 88 because they are similar to homework problems that you will have. Okay, so number 86, if you look in your book, regrettably I'm not in a place where I can display it. So it says a company manufacturing surfboards has fixed cost of $300 per day, total cost $5,100 for 20 boards. Assuming a total cost per day is linearly related, find the equation of the cost function, and then the average cost function, and then sketch, and then what does the average cost per board tend toward? Okay, so let's look at that one. Okay, so what do we know? We are trying, the first thing we know, so as I read through a problem, the first thing I do is I go to a place where it says find. And so it says find the linear relationship. So I know that I am finding the equation of a line. Y equals mx plus b. Except in this case, my y is going to be cost. So you can start with y equals mx plus b. Just know that you're going to be writing it this way at the end. Okay, so what do we know now? Now that we know what we're looking for, now we can look at what we're given and put it in a framework that makes sense. We're trying to translate English words into math. So I know fixed cost equals 300. So that's sort of math, but not quite. This means that when I make no boards whatsoever, my costs are 300. So that's telling me that I have this point. Make no boards, still costs 300. This, you should recognize as the y-intercept, which is, of course, b. Right? What's my second set? I know that I have costs of $5,100 for 20 boards. $5,100. So I can write a point 20 5100. Okay, so I'm trying to find the equation of a line. I need m and b. I can use 2 points, or a point and a slope. I have 2 points, so I can find the slope, so I'll do that. So here come some equations I'm going to use. So I'll find the slope first. So difference in y is 5100 minus 300. Divided by, make sure you keep the order the same. Since I started with this, I need to start with this. 20 minus 0. Try and do some in your head just because it's good for you. So I get 4800 divided by 20, zeros, 240. So 240, what? 240 what? Well, let's look at what this was. This was dollars per boards. So these units are dollars per board. So that is our per board cost. So in the end, our final equation, because I have the y-intercept, I can just go straight. I now have m, I have b. I can just write 240x plus 300. So that is the equation for my total cost. Now let's look at average cost. Remember, average cost we denote with a bar over the top. And all we do is just simply take this whole thing and divide by x. So you were saying, here's my total cost. Remember, this is total cost. This is average cost. So total cost divided by however many boards that I made, that would be my average cost per board. That is different from the added cost per board. This is I've made a set, and now what's the average? This is if I keep making more, I keep adding $240 each time. So slightly different interpretation. Okay, so now we need to graph this. And I am happy for you to do that. I mean, I'm comfortable with you doing that on a calculator. We can also go ahead and do the division. 240x over x is 240 plus 300 over x. All I've done here is just simply split apart the fraction, knowing that these two I can't cancel as it is. I have to split them apart first. Okay, so now we need to graph it. Actually, I don't even need this part or this part because we know that we don't have negative cost or negative number of boards. So, and it actually says to graph from 1 to 30. So let's go ahead and find those values. Let's find average value at 1 and average value at 30. So I'm glad I can do this in my head since my calculator is broken. So 240 plus 300 over 1, so that'd be 540. 240 plus 300 over 30, that would be 10, so 250. So let's go ahead and get those points on. Here's 1, here's 30, and here's 540 up here, and here's, what did I say, 250 here. And so this is going to have, it doesn't actually have, it's going to have a little bit of a curve to it. And it's aiming down. What's it heading toward? Well, as this gets bigger and bigger, we know that a number divided by infinity goes to 0. So eventually, when I get to 30 boards, my average cost is 250. But if I kept making more and more, my average cost would tend towards 240. How else can we do that? Well, we can say, actually, a limit as x approaches infinity. Running out of space, but limit as x approaches infinity of 240 plus 300 over x. Put in infinity, a number divided by infinity, 0, so $240. Okay, and I am going, no, I can finish this one. Okay, so now let's look, that was number 86. Now let's look at number 88. And again, I'm trying to do problems that will be similar to what you have on the assignment. I guess I can use the space now too. Okay, so number 88. Number 88 has a table, so it's talking about energy efficiency in appliances. And so we're looking at the cost of purchasing and operating a 36,000 BTU air conditioner. And so there are two types, the energy efficient model and the conventional model. And the table lists initial cost, let's check this out, list for each. So we have the energy efficient model and the conventional model. So we have initial cost, 4,000 versus 2,700. That makes sense. The energy efficient models are often more expensive. Capacity, 36,000 BTU. That's actually not going to be relevant for us in terms of cost. That just is to make sure we're comparing apples and apples. So we are. We have the same size air conditioner. And then we have the annual cost of electricity. 932 versus 1,332. And so clearly, we spend more money here, but we spend less money per year. Eventually, you might expect them to kind of break even, and then at some point, the efficient model is going to keep saving money, whereas this is going to keep costing you money. Okay, so the first one says, express the total cost and the average cost for both of these. Okay, so let's come over here. Where will I write it? Let's write it over here. So the total cost for the energy efficient model is going to be the initial outlay, $4,000, plus $932 for every year. So in this case, C is total cost, and X is the number of years. So 4,000 plus 932X. And then we can find average cost by just simply dividing that. So average cost. And I'm going to, instead of dividing the whole thing by X, I'll divide this one and then this one separately. So I'll have 4,000 divided by X plus 932. Okay, let's do the same thing for the conventional model. The conventional model starts at $2,700. And now we're adding $1,332 per year. So for every year we add that much more. And now we can do the average cost for that as well. So the average cost, again, I'm just dividing this entire thing by X. I'll do it in pieces. 2,700 divided by X plus 1,332. Okay, I think that's parts A and B. So are the total costs ever the same? Does this ever equal that? Well, let's set it equal and find out. So 2,700, oh, I didn't, so the total cost, right, plus 132X. Let's set it equal to this one, 4,000 plus 932X. So now we need to solve for X. I'm going to subtract this to this side because I'll get positive numbers, so 400X. 4,000 minus 2,700, 1,300. So X is equal to 1,300 divided by 400. Drop the zeros, 13/4, 3.25 years. So because we're saving $400 a year, we very quickly make up the $1,300 difference in price. So a little bit more than 3 years, we break even. The costs, total costs are equal. Before this point, the conventional is saving money because you've spent less to begin with. But after this point, the efficient model is saving you money because now your yearly costs are so much less. Okay, are the average costs ever the same? So we're going to do the same thing, set them equal. So 4,000, and I'm going to do it this way. I'm going to go back to writing it this way. Is this, I'm just doing the whole division. Remember, for the total cost, we can divide the whole thing by X. So are those ever equal? So, I'm trying to think the best way to explain this one.